Good afternoon, everyone, and welcome to this ENEFIRST webinar on local energy planning for commercial areas, what role for the energy efficiency first principle. I'm Margot from the Buildings Performance Institute Europe, and today I'm joined by Jean-Sébastien and Tim from the ENEFIRST project. We'll have a bit more people joining in a few minutes, but for now, I'll just like to give some housekeeping instructions. Before we get started, I'd like to show you how we participate in the event. So on your screen, you should see the screenshot of the attendee interface. So that's what you should. This box is what you should have on the upper right corner of your screen. So you're listening using your computer speaker system by default, but you can also join by phone just by clicking on the telephone in the audio panel. So you'll have the opportunity to submit questions into the question box that you can see in the panel. We'll have two different Q&A sessions, so we'll basically collect your question and answer them during the Q&A sessions. We'll also send you the slides and the recording tomorrow by email, and it will also be available on the ENEFIRST website. So that's basically it. In terms of the agenda, we'll have a short introduction of the energy efficiency first principle and the ENEFIRST project by Jean-Sébastien. And then we'll have the main presentation by Tim on local energy planning for commercial areas, where we'll have two different Q&A sessions. So don't hesitate to ask questions during the whole webinar, and we'll collect them. So I think that is all for the agenda. In terms of the webinar series, this is actually the second webinar of a series of 3 webinars. The last one is coming up on Wednesday, the 27th of April. So you can still register. I'll send you here you actually have the link to the events. And if you want, you can also check the presentation slides and the recording of the previous webinar, which took place, I believe, about 2 weeks ago, about district heating. So that's also available on the website. So I wish you a nice webinar. I would like now to hand over to Jean-Sébastien, who will give an introduction on energy efficiency first and the ENEFIRST project. Jean-Sébastien, the floor is yours. Thank you.
Thanks a lot, Margot, and good afternoon, everyone. Thanks for joining us for this new webinar. A very short introduction about energy efficiency first. I guess most of you are by now already familiar with this concept. Next slide, please. So within the project, in addition to the definition that you probably know from the governance regulation for the Energy Union, we specified a bit more the principle to highlight some key components from our own analysis of the background of this principle. So one is that is a decision principle. So it means that you compare different options and that this comparison should be fair. So that's the equal opportunity aspect that is highlighted on the bottom. And at the end, all that is to give priority to demand side resources whenever it is relevant. And relevant here means more cost effective, adopting a societal perspective. Next slide, please. So that can be illustrated in 2 ways. The first one is to consider the energy systems as a whole. So not looking at the 2 sides in silos, so the supply side and demand side, but adopting a comprehensive view and combining them all together. And when an investment related to energy is needed, to consider the different options on both sides. So not only, let's say, if you need to prepare your energy planning in particular, not considering only the development of new generation capacities or new networks capacity, but also thinking about what can be done to use more efficiently energy and to reduce the demand for energy. Next slide, please. And the other aspect is when doing these comparisons between the different options to adopt a societal perspective. What do we mean by that? Mostly two things. The first one is to consider multiple impacts, which means all the impacts that can be relevant from the point of view of the society, and not only from the point of view of the individual investors or end users. So that's one side, and the other side that is always also related to taking the society point of view is to adopt a long-term perspective. So not only let's say the short-term perspective that you could have looking at cost effectiveness from an investor point of view, but looking at the long-term goals like the climate neutral goal of the energy union. Next slide, please. How to implement this principle in practice? We came out with these 3 questions that can form a kind of checklist to keep in mind when you work with that and when you try to see how this principle would fit with your own practices and your decision processes, let's say. The first one is to make sure that all options are considered. So in particular, demand side resources are considered as part of the alternatives when deciding about a new investment or a new equipment. The second one is to make sure that the comparison is on a fair basis, as I said earlier, in particular considering a broad scope of cost and benefits. And the third one is making sure that the decision-making rule is not biased, and so that there is no priority that would be given beforehand before the analysis to one or another particular option, and at the end, when relevant, priority is given to demand side resources. So that, let's say, the 3 steps or 3 questions to keep in mind when dealing with this principle. Next slide, please. About the project itself, ENEFIRST, that's part of a call for project to make the energy efficiency first principle operational. Next slide. And the overall objective is to develop policy proposal for the implementation of the principle. And you have different, let's say, specific objectives to achieve that. And one is about quantifying the potential impacts of implementing an energy efficiency first, and that's the topics of this series of webinars, including today. And another important point about ENEFIRST is that it's focused on buildings end use and their energy supply. You have also on the bottom of the slide that you can get then on the website other initiatives and other resources on the energy efficiency first principle, and especially other documents that cover other sectors than buildings. Next slide, please. So basically the project is structured around 2 streams of analysis. One that is more quantitative and based on modeling. That's the one that is presented today. And the other one is related to policy analysis. We have 7 partners in the project. ICP is coordinating. Fraunhofer, that is represented today by Tim Mundell, is leading the modeling part together with TUVIN and IRIS. Both partners have also a webinar. So IRIS was the previous one and TUVIN is the next one. And on the policy analysis part, you have 3 other partners, RAB, BPIE, and CEU. But all together, this team is working on both sides to ensure coordination and a joint approach. Next slide, please. In addition to this series of webinars about the part that I mentioned on quantifying the impact of implementing energy efficiency first, you can also look at the website to find the proceedings of the workshop that was organized last February and that presented the results from simulating 3 EU scenarios. And you will see today that this webinar series is more about more specific modeling case studies that Tim will present one in a minute. And if not done yet, book in your agenda the 31st of May and the 1st of June. to meet us in Brussels for a joint conference organized together with the Synergies project. And most probably by the end of the month, you will find more details on our website about that. Next slide. And that's just a screenshot of the ENEFIRST website. There are many resources that you can find there, and that's to encourage you to have a look after this webinar if you want to know more about the principle and what we offer to support this implementation. And that's with that, I think the scene is set. And Tim, the floor is yours to present us today's modeling case studies.
Thank you, Jean-Sébastien. So I'll be just sharing my screen. I hope this works.
Yes, we see it in full screen. Perfect.
Great. So hi, everyone. Good afternoon. My name is Tim Mandl from Fraunhofer ISI, and I have the great pleasure today to present you the outcomes of our model-based analysis on commercial areas. Here's a bit of structure for the following minutes. So we will begin with a little bit of background on why there's a need for model-based assessments on commercial areas in the EU. We will then continue with a bit of methodological background on this analysis. That means the scenarios, the model, and the relevant input data, followed by a short Q&A session in which you are warmly invited to ask anything that's on your mind about the methodological aspects or the background. There will also be another Q&A session, of course, after I've presented the results and the discussion. As I've said, there will be some results, so in which we're going to show that building retrofits basically do pay off for commercial areas, but there are certainly limitations. And finally, there will be a discussion on why these results, as with every model-based analysis, should be interpreted with a bit of caution. So a bit of background. Why is there a need for model-based assessments on commercial areas in the EU? Basically, there are three rationales, if you will. So on the one hand, there's the societal relevance. The services sector, which includes offices, schools, and restaurants, etc., represents about 14% of final energy consumption in the EU. And much of this energy is used in existing buildings that are characterized in general by very low energy performance. In response, the energy efficiency first principle that Jean-Sébastien just introduced has been gaining some momentum lately in EU energy and climate policy. For example, in the Commission proposal for the recast of the Energy Efficiency Directive. In parallel, there are a lot of other activities, including the renovation wave strategy, of which the objective is to at least double the annual energy renovation rate of buildings by 2030 and to foster deep renovations in the building sector. This has a couple of ramifications, for example, for the EPBD proposal, as well as for the EED, which suggests, for example, the aspect of local heating and cooling plants for municipalities greater than 50,000 inhabitants. That's the societal relevance. There's also local relevance. So urban planning authorities and energy planners, if you will, they require some comprehensive view of cost-effective opportunities to improve the performance of buildings at the district level. There are a lot of technical opportunities and technical options there, ranging from building retrofits itself to the on-site use of renewable energy-based resources, for example, PV, solar thermal panels, different types of heat pumps, etc. There's large infrastructures or also microgrids for district heating and cooling, which include cogeneration, again, heat pumps and other technologies, up to the utilization of waste heat, installation of storages, demand response strategies, and much more. So in the framework of the efficiency first principle, these are all resource options that should be taken into account ideally in order to come up with a socially beneficial configuration of technology options. And finally, of course, there's some scientific relevance to this. Urban planning basically requires reliable tools to assist this overall optimization process for energy systems. And in technical terms, this study of optimal energy system configurations at the local level is on the one hand a multi-objective problem, because there's not only the target of reducing greenhouse gases, but also to ensure cost effectiveness, to minimize initial capital expenditures, for example. But it's also a multi-scale problem. We're not only dealing with heat, but also with electricity systems and gas. So overall, this requires some detailed, also spatial temporal modeling in order to account for the variability of renewable energy resources. That being said, what's the objective of this case study? So basically, we are exploring the trade-offs and synergies between building retrofits on the one hand and various energy supply options on the other hand in commercial areas. These energy supply options include on-site generation, but also district heating and microgrid solutions. These are some of the key characteristics of this analysis. So what we do is that we have one archetypical commercial area for 3 EU countries. I'll be showing in a second what this means. This is inspired by real-life buildings and topography. We use an open source modeling software for analyzing possible system configurations and their cost effectiveness. And this whole analysis is characterized by an hourly resolution of system operation, which basically accounts for, which enables us to take into account the variability of renewable energies and also other aspects that are relevant to system operation. So let's have a look at the methodology. I just mentioned this archetypical commercial area that we're examining. Here's an illustration of this. This is actually a real-life area situated in the city of Karlsruhe, which is basically the hometown of the institute that I'm working for. What do we mean by archetype? So we take this this local area, but basically assume that this is a fictitious area, but we also use it for across these 3 countries that I'll be showing in a second. And then we basically characterize this this office park in terms of buildings that are situated there. On the one hand, we have a variety of office buildings, which could look something like this. So built in the approximately in the 70s, very poor energy performance. We've also got one school located here, which looks similar. And then there's a couple of miscellaneous buildings, including a laboratory, also a canteen for the people working there, as well as a server room, which is interesting because the waste heat from the data centers can be potentially used in the local microgrid. So that's this archetype office part that we're dealing with. And then, as I said, we apply this archetype to 3 countries, which then has implications for the cost of energy, for weather conditions, and other aspects. In particular, we look at the city of Frankfurt in Germany, the city of Budapest in Hungary, and the city of Malaga in the very south of Spain. And as you can see here from these temperature charts, these countries obviously differ by the annual or the monthly average temperature, as well as minimum and maximum temperatures, which has obvious implications for heating demand. But as I've also mentioned, by looking at these 3 different countries, we take into account differences in cost and also, for example, differences in the efficiency of heat pumps and other aspects. So what did we do with this archetype office park and the 3 countries? We defined a range of 3 scenarios for each country, which are called existing, standard, and advanced. What does that mean? In the existing scenario, we assume that buildings within the local area stay the way they are. That means we have these buildings from the 70s, which with very low performance. But then on the other hand, we're planning a completely new energy supply system for the neighborhood. That's the first scenario. The second scenario involves what we call standard retrofit of the building. So this is a thermal refurbishment of the building components, but with limitations when it comes to the implementation ambition, if you will. And finally, we have an advanced scenario which corresponds to a deep retrofit of the building stock. So what's the point about these 3 scenarios? The lower basically the heating demand is within the buildings in response to the thermal retrofit, the lower is also the need for energy supply, obviously, but this also has implications for the capacities that need to be installed, and finally for the overall system costs, which makes this analysis interesting because it allows us to investigate this trade-off between technology options. Let's have a closer look at the assumptions behind these scenarios. So if we just focus on the case of Germany here, we defined basically a renovation package for the roof, the walls, the floor, and the windows of these buildings. And here below you see the U value for the thermal transmittance of these building components. And if we take the walls as an example, we have concrete panels in the default existing scenario, and then we add 12 centimeters of insulation and 24 centimeters of insulation in the standard and the advanced scenario. All of these building components have specific costs, which are included in the model. And in the end, we add everything up to some cost effectiveness analysis, and then we're going to have some interesting outcomes of this assessment. But to continue, what we use in terms of energy modeling software is the so-called City Energy Analyst. The CEA was developed by the ETH, the Swiss Federal Institute of Technology, and it's a Python-based open source energy simulation model, which includes functionality to simulate building energy demand, solar radiation, energy potential assessment, and much more. More specifically, here are a couple of key features of the model. First of all, there's a data helper. So this contains the georeference information of buildings and their surroundings. This data is gathered from OpenStreetMaps, and it includes building properties such as the footprint area, the height, the year of construction, and more. Second, there's an urban solar radiation tool, which is a dedicated engine to compute the hourly solar radiation onto the facades, but also onto roof surfaces, taking into account mutual shading between buildings. Based on that, there's a renewable energy assessment. So basically, the model computes the resource potentials for different renewable energy sources. So this includes rooftop solar potentials, ambient heat, which includes geothermal heat and lake water and sewage water, up to waste heat from servers and industrial processes. There's also a dynamic demand forecast. So CEA uses a building by building simulation approach, and each building is modeled using its real location, which in this case is a fictitious location, but given the weather conditions that we assume, we make it a somewhat real location. And it also uses the geometry with the construction properties that I just mentioned in the previous slides. Finally, or not finally, almost finally, there's a multi-objective optimization. What does that mean? So that is basically, in mathematical terms, a mixed integer and non-linear program. And this algorithm configures a local energy system for minimum total costs, for minimal emissions, and primary energy needs. So these are three objectives, if you will. So overall, what the model computes is not a single overall optimum, but a set of feasible solutions along a line of possible system configurations. I will be showing that in 2 slides, I think, what this means in practice. Finally, there's a mapping and visualization tool that I will also briefly show. The CEA contains open source libraries in Python to automate graphs and time series data, and we will be taking advantage of that in the following. Some quick notes on the input data. There's some default data included in the model, but we used dedicated data for single items. Building properties are based on the 2013 Tabular project. Retrofit costs are based on the Entrance project, which is also a couple of years old, but we use construction price indices to refer the cost data to the year 2022. Weather data, you've seen that in the previous slide. Technology cost is compiled from the ResHeat project and the Danish Energy Agency's technology catalog. Energy carrier prices are based on Eurostat and the ENEFIRST project, in which we have scenarios for the EU overall, in which provides us an estimation of the cost of district heating and electricity and other energy carriers until 2015. Same goes for the emission intensities of electricity in the mid-run until 2015. This leads me to a quick break and the opportunity for you to ask me anything about the methodology or why there's a need for such analysis. So if there's anything on your mind, feel free to type it in the chat box.
Thanks, Tim. There might be a first question if you come back to your previous slide about one point you mentioned about the data sources, and especially the one on retrofit cost. So you mentioned that it might be a bit old now. So would you say that the fact that it's more complicated to find data for the building retrofit cost compared to the supply side cost for options on the supply side, can this create kind of bias when you compare the different options?
Yeah, overall there's always a bias when you have to rely on building retrofit cost, because it's strongly dependent on material costs and also labor costs, which on the one hand country specific, but then on the other hand, when we talk about local conditions, ideally you would even have to be more specific about the local circumstances. That being said, the entrance project, as I said, I think the data is from 2012 or 2013, but we use these construction price indices from Eurostat to make the data as recent as possible and to take into account inflation that's happened in the meantime. And this Eurostat construction price index takes into account changes in material costs and labor costs and other price components. So I would argue that it's a very reasonable proxy to actual retrofit costs, but in practice, I'm sure there's a lot of variance that is possible in these costs. But you've also mentioned the cost of energy supply. I think that's the same story. Perhaps a heat pump in itself is more or less costs the same in Germany as it does in Spain, but the difference is probably the different labor costs in these countries. So, but we attempted, let's say, to take these differences into account as much as possible.
And maybe the second question would be the specificities when looking at commercial buildings compared to residential buildings. I assume that there is a much higher use of air conditioning in commercial buildings. So did it make this case study, for example, a bit more complicated compared to looking at residential buildings, or how did you approach that?
Commercial buildings are different indeed from residential buildings, and unfortunately, much of the research in previous years has focused on residential buildings and kind of neglected the commercial ones, which was challenging, for example, when defining adequate building properties for the building envelopes. But when it comes to the occupancy, let's say, and the building usage, we could heavily rely on the CEA model, which contains a dedicated module for building occupancy. And then within the model, you just need to select what kind of building it is, whether it's a residential building or laboratory, let's say, or an office building. And then based on that, as we will be seeing later when it comes to charts that operate on an hourly level, we can very nicely see that buildings are not these buildings are not used 24/7. There's minimum load here and there for some electrical appliances, but overall there's no need to heat these buildings 24/7 because office people tend to come at 9 and then leave at 5. There are some exceptions to that, of course. But that's certainly taken into account. We're not dealing with residential buildings. Yes.
Yeah, different patterns. Yeah, thanks, Tim. If you want to continue, I think we can take more questions later on then.
Sure. Yeah. Thanks a lot for your questions so far. But let's move to the interesting stuff, the results of this analysis. What I would like to do in the following is to focus, at least for now, exclusively on the case of Germany, because these results are very detailed, and I think it would make more sense to have a detailed view on one of the countries. And then once a report that is related to this webinar is out, you can also take a look at the results for the countries of Spain and Hungary. Well, let's get started with something rather simple. I would say what you see right here is final energy demand in megawatt hours per year for these three scenarios: Germany existing, standard, and advanced. These numbers are quite straightforward. We have very ambitious building retrofits in the advanced scenario, which is why energy demand for space heating strongly decreases. It's actually decreased by 72.3%, which can definitely be called a deep retrofit. Whereas we have something like a medium or light retrofit in the standard scenario, which is still almost 60% reduction in final energy demand for heating. What is hardly visible in this chart, but which happens in the model, is that space cooling demand slightly increases from the existing to the advanced case, because basically the internal gains from electrical appliances, but also the heat that office workers emit, is being trapped within the building, which leads to a slightly higher cooling demand. But this is not in the focus of today's presentation, or in the focus of these results on Germany. Whereas once the report is out, once you look at the when you look at the results for Spain, for example, there are some interesting ramifications on space cooling demand and district cooling networks. So overall, key message here, according to this bottom-up model, thermal retrofits lead to a significant reduction in final energy demand for buildings. This is not super groundbreaking in itself. Same goes basically for the district load curve. This is the district load under nominal operating conditions. So in the existing, or across these three scenarios, before we define any optimal solutions or so, we assume that natural gas boilers are basically installed within the system, and this is the load curve in final energy terms for these three scenarios. Actually, peak load in this average year occurs on 20th of February with an average outdoor temperature of minus 4.5 degrees Celsius. And we can see in that day, or this hour, that peak load reduces from 138 megawatt hours per day to 82 and 70.9. So again, key message is that building retrofits also reduce peak demand, and thus, as we will be seeing later, the capacities needed on the supply side to meet heating demand. What you see here is a possible district heating network layout for the example of the existing scenario in Germany. So basically what the model does is that it computes the potential layout of a network with a minimum spanning tree algorithm. And it also computes the water flows between these network branches, or these trenches. So trench length, according to the model, is between 70 centimeters and up to 103 meters, which could be somewhere up here. It also computes the mass flow rate in kilograms or liters per second, the peak velocity. So overall, according to this simulation, a thermal hydraulic network is technically feasible for all of the buildings in the area, and the same goes also for the other scenarios. These are only, however, technical potentials. This does not tell us yet whether this is a cost-effective solution to meet heating needs. I will be getting back to this in a second. But first, let's stick to the technical potentials. What we see here are solar generation potentials for photovoltaics and rooftop solar thermal installations. Here in the gray shading, you see solar radiation in megawatt hours per hour, so which can be interpreted as the power in megawatts. Total space available on roofs comes down to about 24,000 square meters, which is about 150 times 150 meters. We can see here the technical potentials for photovoltaics and solar thermal installations. And the key message here is that different technically viable solar technologies compete for limited roof space in the neighborhood. You may wonder why these technical potentials for both PV and solar thermal are so low. They are in laboratory conditions, there have been PV panels with an efficiency up to 40% or something, but this is strictly under lab conditions. The model takes into account, on the one hand, the angle of the solar radiation, But also we know from practice that the efficiency of PV panels, for example, deteriorates with increasing temperature. So a PV panel in peak summer times won't be as efficient as in, oops, that was too fast, won't be as efficient as in wintertime, for example. And these very detailed technology-specific aspects are properly taken into account in the model. But let's move closer to the question of how these local systems should ideally be designed to meet heating needs at the lowest possible cost. What you see here is a chart that compares the total annual cost for energy supply on the horizontal axis with the annual CO2 emissions that are associated with different technology configurations. These curves that you see right here correspond to the 3 scenarios, and each dot on the curves represents one unique system configuration, which has a particular cost per year and a particular level of greenhouse gases. So this chart can be interpreted in 2 ways. On the one hand, we can take a vertical perspective, and which enables us to see that higher levels of greenhouse gas reduction are possible basically for the same cost when we follow for example, the advanced scenario. It's important to emphasize here that this is only the cost for energy supply, and it does not yet take into account the renovation cost. This is something we will be looking at very end, but it already shows very nicely that when we add the horizontal view, that basically for the same level of greenhouse gases per year, we need the cost of energy supply is lower. Overall, the greenhouse gas levels of these system configurations are somewhere between 500 and 2,000 tons of CO2 per year, and costs range between 2.9 and 5.6 million euros per year, which is quite a difference already. You may wonder why greenhouse gases do not go down up to 0. This is because we here represent the average CO2 intensity of all energy carriers up until 2050, which also implies that electricity, at least now, is definitely not carbon neutral. But we assume that it's carbon neutral by 2050, but that's why overall there's literally no energy carrier besides biomass, for example, which is limited, however, that would enable a true level of 0 greenhouse gases. So overall, we can see here that in each scenario, buildings can be supplied by a variety of technically feasible technology configurations. But what is perhaps most interesting in the context of the efficiency first principle is that is whether energy efficiency options can achieve the same outcome at a lower cost. And this is what we do by, in the following, looking at 3 particular resource configurations for each of the 3 scenarios, which all end up with roughly the same greenhouse gas level of about 800 tons of CO2 equivalents per year. So these 3 dots that you see right here are going to be disentangled and illustrated some more in the following. In this chart, to begin with, we see the hourly heat dispatch. So here in these Lego bricks, if you will, you can see the different technologies that are dispatched at an hourly level on the 20th of February in 2022, which, as I've shown previously, was according to the average temperature series, the day with the lowest temperature or the highest heat demand or heat load. We can see that in these 3 scenarios, base load is covered by biomass, CHPs, and peaks, especially here in the existing case, are served by natural gas boilers. And we can see very nicely that peak thermal load reduces by about 50% in the standard scenario and more than 70% in the advanced scenario. So building retrofits clearly reduce district heating peak load and also alter the composition of cost-effective technologies. For example, here in the advanced scenario, there's no need anymore for ground source heat pumps to meet heating demand or heating load. And again, a brief reminder that all of these scenarios are reaching the same greenhouse gas levels in the long run, but just with different means. A similar thing can be observed for electrical dispatch and electrical load. So what's going on with the power system? Here in this chart, everything that is above the x-axis is load that has to be supplied, and everything below the x-axis is pretty much demand on the consumer side. As you can see here in these gray shaded areas, there's a continuous demand for appliances and other appliances and lighting, for example. But also we again recognize the heat pumps, which have to be utilized. And here in this purple shading, there's also what is also taken into account is the variable load for district heating network pumps, which can be up to 0.22 megawatt hours per hour. And we can also see here on the positive side of the chart that most of the electricity needs are being met by grid imports, whereas a small share is covered by photovoltaics and biomass cogeneration. So overall, building retrofits do not only reduce thermal load in district heating networks, but also electrical load. So let's have a look at the big picture. What you see here are the installed capacities for the 3 scenarios for this entire average year. We can see quite clearly that heat generation capacity reduces by 40% in the standard case and almost 50% in the advanced case, because heating demand is just significantly lower due to the building retrofits. And we can also see that on-site natural gas boilers are a significant technology, particularly in the advanced scenario. So these on-site natural gas boilers are not connected to a district heating network, but they are operated individually. I will be showing you very briefly what this means in practice. So what we see right here is some direct output from the CEA model. Right here at the top, you see the cost optimal network layout for the Germany existing scenario, in which almost all of the buildings are connected to the district heating model, to the district heating system, also including the school that is quite far located here at the top. But things look different already when we look at the standard scenario and more extremely the advanced scenario, in which only a few of these buildings are still connected to the district heating system, because according to the model, it does not make sense anymore from a pure cost perspective. As a local planner, you may assume or you may argue that if you build a district heating system, you make sure that each of the buildings is connected. But from a pure cost perspective, according to the model, this does not make entire sense. Let me go back to the slides. Oops. This should be gone. Excuse me. Where was I? Right. So overall, what we did so far is a pure technical analysis, but perhaps the most interesting question in the scope of efficiency first is whether these building retrofits actually pay off. So what we did is to have a basic economic analysis from basically the perspective of those who own the buildings and the supply assets. The 3 metrics that we look here to assess the attractiveness of the investments are the net present value. Oops. No, that was too fast. Here, the net present value, which is a very basic indicator of investment appraisal. It compares the initial investment for the building retrofit. This right here is the capital recovery factor, also called the annuity factor, which is a function of the discount rate in the lifetime of the building components. And it compares this initial investment with the discounted reduced cost for energy supply. And in order to be cost effective, the net present value basically needs to be positive. There are 2 derived indicators which basically tell the same story. One is the discounted payback period. So that's the number of years needed for the investment to amortize or to pay off. And the other is the internal rate of return, which is the discount rate that makes the net present value 0. And if the internal rate of return is greater than the discount rate, or also called the hurdle rate, then the overall investment is cost effective. For this economic analysis, we assumed a discount rate of 5% and a lifetime for the building components of 20 years, according to the EPBD. So what we see is that, interestingly, the standard scenario is not cost effective. The net present value is negative with about 225,000 kilo euros per year. The payback period is close to 30 years and the internal rate of return is very low. Whereas for the advanced scenario, we have a positive net present value of almost €500,000 per year. The whole thing pays off within 13 years, and the internal rate of return is quite high with 8.42%. So overall, the standard scenario in this case is not cost effective, but the advanced scenario is. So why is that the case? Since the ambition level is much higher in the advanced scenario. This is because building retrofits are characterized by a very large fixed cost component, and regardless of whether you attach 10 or 15 centimeters of installation, you're still going to have these fixed costs in every case, which is taken into account in these calculations, and which surprisingly supports the idea that deep retrofits are actually a very attractive thing to pursue for local commercial areas. I'm going to speed up things a little. Here is a brief discussion of these outcomes, or why these results should be interpreted with caution. One thing that we already mentioned is uncertainties. So of course, we do not know the future cost of each and every energy carrier. There's uncertainty about climate conditions, about energy carrier prices, technology costs, etc. That is quite straightforward. Second is, while the model in itself is very sophisticated, there are of course some features that it does not contain. Let's say we do not have dedicated modeling of the local power network, which could also, if that was included, could have some interesting implications for the cost of electricity supply. Direct rebound effects are not explicitly taken into account. Basically, what we assumed is a stable indoor temperature regardless of the retrofit ambition. And finally, while there is some scope for demand response, both in electrical but also in district heating systems, this was not in the focus of this assessment. And finally, there's some aspects related to cost-benefit accounting. So our economic analysis was basically based on capital expenditures and operating expenses, but it did not take into account the hassle or the search and information costs for figuring out what is actually the most performative system configuration, and let alone the organizational cost for retrofitting the entire area. We also did not take into account these aspects that are constantly referred to as multiple impacts in the efficiency first debate, including comfort gains, reduced air pollution, increased real estate value, and local employment. If all of these aspects were taken into account, this could possibly shift the outcomes of the economic analysis. To conclude, what we found is that local planning for low carbon energy systems involves a trade-off between saving and supplying energy. And building retrofits, as I've shown, reduce the magnitude of energy needed and thus also the generation capacities and the overall cost for energy supply. However, retrofits also involve significant capital expenditures that can be burdensome, as we've seen with the standard scenario. There's a clear scope for energy efficiency first in local planning for commercial areas. Deep renovations can be more cost efficient in meeting equivalent greenhouse gas reductions than light renovations or strategies that focus exclusively on supply side investment, as it was the case with the existing scenario. We've also found that energy efficiency first should not be equated with end-use energy efficiency within buildings. This is because heat pumps, cogeneration, and efficient district heating overall are a key requirement for achieving significant greenhouse gas reductions in commercial areas, and overall supply side energy efficiency is key, just as end-use energy efficiency is. And finally, as with every model-based analysis, these results should be interpreted with a pinch of caution. The problem is not only uncertainties, but also the capabilities of the model setup, as well as conceptual issues in counting costs and benefits. This leads me to the end of my presentation, and I'm very happy to take questions.
Thanks a lot, Tim. I think that's a very, very interesting case that actually raised many questions. So maybe the first one that can come with one of your main result or conclusion that the advanced scenario can be more cost effective. So this results is from a total system cost perspective, right? And would the result and the conclusion be the same from the point of view of the building owner or the investor?
These are very different perspectives that unfortunately we did not explicitly take into account in the analysis. Yeah, there are a couple of details that would need to be made clear before answering this question, including the question who owns the building. If it's tenants, then I suppose that there won't be big changes in the cost of energy supply overall. But if the building owner is also the tenant, then there's different implications. Long story short, I cannot fully answer that question, but I would assume that positive effects would also be visible both for the investor and the whoever is the building owner in the assumed case. But this would require some dedicated analysis that was beyond the scope here. Yeah.
Sure. And for following up on that, does it mean that these results would support a stronger regulation for the renovation of commercial buildings? If the case is that the advanced scenario is more cost effective for the society.
Are you referring to stricter building codes, for example, or minimum performance standards?
Yes, or the equivalent that is suggested in the current proposal for the EPBD recast to have a minimum energy performance standards for buildings. Yeah,
I mean, the tricky aspects about building codes and minimum energy performance standards is always to infer from a single case to an entire country or even an entire continent. So the results that we've computed here, they hold for the very specific case of this local area with local resource potentials for energy supply, local climate conditions, and much more. So I would be cautious about overly inflating these results, let's say, and deriving too much from that when it comes to nationwide building codes, for example. But it does provide some support for the idea that the building owners, or if there's an integrated asset owner who owns both the buildings and the local heat system, that there's definitely some scope for cost-effective building retrofits. And whether we want to enforce that by means of minimum energy performance standards, that's a question of appropriate instruments. But at least from this analysis, yeah.
So you mentioned the influence of different climate conditions. So I guess the results you presented here were mostly for the German case, right? So are the conclusions the same for Spain? Because in the beginning you've shown that the climate conditions were quite different. So do you have the same conclusion that the advanced scenario is also more cost effective in let's say in a country with a milder or even warmer climate?
Yes, actually, at least for Hungary, we get pretty much similar outcomes. Whereas for Spain, things are a little more tricky, because what we picked is a location in very south of the country with a very warm climate, which definitely does not provide much potential for reducing thermal energy demand, or let alone for installing a district heating system, because the heat demand is just particularly low. However, the model also computes some possibilities for a district cooling network. However, the technology options that are taken into account in the model are very limited, and which is why we did not see huge differences in the overall cost between the three scenarios, and especially the advanced scenario did not fully pay off, because probably the ambition levels that we assumed for the country of Spain when it comes to the building envelope were much too ambitious. You don't need triple glazing in the south of Spain, for example, if your heat demand is very low. And of course, this has some implications for cooling demand, but cooling demand is much more dependent on the building materials, for example, and shading systems installed. And these are aspects that we did not explicitly take into account. Which, however, could be modeled in the CEA model.
Right, that's a good point as well, that there can be a bias in the models, that they have much more options for space heating than cooling for the moment, and probably that will change very soon, because there will be a demand for more and more modeling for space cooling. Another question is related to what you've shown as an impact of a lower demand, and making that in some cases, basically on your particular example, that for some buildings that will not be cost effective anymore to connect them to the district heating. Is it in a scenario where the district heating would need to be built, or is it also applicable in case the district heating would already be there?
Well, basically what the model does is to follow a so-called greenfield approach. So it assumes that the system is not already there, and that things are basically constructed from scratch. So overall, the storyline behind these scenarios was that we have these very old buildings from the 70s, including the heating systems that are definitely outdated and need replacement anyway. And we assume that natural gas boilers are in place. But then the question is, like, if we had all options at hand, which path should we basically follow in order to ensure least cost energy supply for this commercial area? And that's where these newly built district heating systems would come into play. I think there's also the option in the model to assume that a district heating system is already there. But for the sake of having pronounced results, let's say, we assume to build everything from scratch and then see what implications this has for costs and benefits.
Okay. No, that's clear. And that was just to clarify that the conclusion you mentioned on that was in a scenario where the district heating network will need to be built. I assume that the conclusion would be quite different in case the buildings are already connected to district
Certainly.
heating.
Yeah.
Okay. No, because it could sound a bit strange then. And also another thing that can raise question is that you mentioned natural gas boilers as part of even the advanced scenario, but would they be in place until 2050? Or because that sounds strange to see still natural gas boilers.
Yeah.
If the objective is to achieve carbon neutrality by 2050.
Yeah, definitely agree. Maybe to clarify this, what we the detailed charts that I've shown on the installed capacities, etc., they were referring to these three particular system configurations right here. But we can see that there are also other system configurations below which achieve even lower greenhouse gas levels. And these, I don't know by heart which technologies are behind these individual dots, but I would assume that natural gas boilers do not play a role anymore in many of these. But basically, by looking at these three particular points, we had this common greenhouse gas reduction target, which is one of the underlying ideas of the efficiency first principles, to achieve basically the same outcome, but with lower cost by relying on energy efficiency. So long story short, whether natural gas boilers are still going to be in place up until 2050 is, of course, we've got a political consensus that this shouldn't be the case, but from a pure individual rationale, be it a building owner or a local community, who take a dedicated cost benefit perspective, I would still see some work there to really make, in this case, natural gas boilers as unattractive as they need to be in order to reach the 2050 target.
And on this graph, the level of emission that we see, that's the level that is achieved and after all is implemented, so that would be the level of emission in 2050.
No, these are actually average emissions from now. I think we started in 2020.
Okay.
From now until 2050. So
okay, so average annual emissions over the 30-year period.
Yeah, and there's no stock turnover or anything involved. So basically, what the model would do is to if any asset, take a PV module for example, reaches the end of its lifetime, it's just going to be replaced with the same technology. So that's the idea behind these average costs. So in reality, if you had an entire country or so, there's some turnover at a yearly basis, but here for sake of simplicity, we assume like a constant technology configuration until 2015.
Okay, thanks a lot, Tim. And I see Margot that is right to remind me that we have reached the hour now. So unfortunately, we cannot take more questions, or maybe there is no. I think that's okay. We cover most of them. So thanks a lot, Tim. I don't know, Margot, if you want to say a final word to the participants.
Yeah, very quickly, thanks for attending this webinar. We'll be sharing the slides and recording tomorrow by email, and it will also be available on the website. And I think that's all. We'll have the final webinar on the 27th. So I've already included the link in the chat, so feel free to register. And thanks again for today, and have a great afternoon. Bye, everyone.
Thanks, Margot. Thanks a lot, Tim. That was very interesting. And yeah, looking forward to meet everyone in 2 weeks to speak about stage renovation between at-once renovation. All right.
Great. Thanks.
Okay.
Bye.